Hello, welcome to Lecture 7, Resilience and Mitigation, part of the Safety-Informed Security Lecture Series for Cyborg. In this lecture, we move from identifying threats to asking what the system should do when prevention is not enough. The focus is resilience. In safety-informed security, resilience is not simply keeping a device online. It's about maintaining safe, constrained, observable, and recoverable operation when faults, attacks, disruption, or uncertainty affect normal behavior. This lecture maps to several cyborg knowledge areas. It maps to cyber-physical security system. It also maps to the security operation and incident management and risk management and governance. And it partly covers network security, physical layer and telecommunication security, and authentication, authorization, and accountability. The lecture is organized around 5 areas. We're going to first define resilience in safety-informed security and distinguish it from prevention. We're going then to consider degraded operation, including graceful degradation, fail-safe behavior, fail-secure behavior, fail-operational behavior, and local fallback and manual override. We then examine mitigation patterns for wireless and IoT systems. This includes defense in depth, segmentation, authentication, replay protection, rate limiting, secure updates, and configuration control. We then look at redundancy, diversity and fallback, including voting, plausibility checking, common mode failure, and alternative communication or sensor paths. Finally, we discuss monitoring detection, incident response, recovery, assurance impact, and residual risk. Let's start first by defining what is resilience in safety-informed security. Resilience is the ability of a system to continue providing an acceptable level of service when faults, attacks, disruptions, or uncertainty affect normal behavior and normal operation. In safety-informed security, this definition needs careful interpretation. A resilient system is not simply a system that continues running at all costs. A system that keeps operating while accepting untrusted data, executing unsafe commands, or hiding failure from operator is not resilient in the context of safety critical sense. The system must remain safe, constrained, observable, and recoverable. Safe means it avoids behaviors that could harm people, equipment, or the environment. And constrained means the system operates within defined limits when trust is reduced. Observable means operator, maintainer, or automated monitors can see that something abnormal has happened. Recoverable means that the system can return to a trusted state through defined checks and procedures. The key idea is that prevention may be incomplete. Security controls can fail, attacks can bypass defenses, and faults can occur in unexpected ways. Resilience asks what the system does next. So we move from prevention to resilience, and prevention and resilience are related, but they're not the same. A prevention focus tries to stop unauthorized access, block malicious traffic, prevent unsafe commands, and harden devices and networks. These controls reduce the likelihood of failure. However, a resilience focus assumes that some failure may still occur. It asks how the system detects abnormal behavior, limits the effect of compromise, maintains safe degraded operation, and recovers with evidence and assurance. And the distinction matters in safety-critical IoT because prevention alone is rarely sufficient. Wireless links can be jumped, credentials can be compromised, sensors can fail, cloud services can become unavailable. Devices may operate for years in environments that change after deployment. And prevention reduces the chance that a security failure happens. However, resilience reduces the safety impact when failure still occurs. The question is therefore not only whether an attack can be blocked, it's also whether the system remains safe if the attack was not blocked. So, let's have a look at this diagram of security failure and safety impact. So this diagram shows a path from security threat to safety outcome. A threat may involve spoofing jamming, tampering, replay, unauthorized access, or manipulation of firmware or configuration. This can produce security failure, such as false data, a lost link, or an unsafe command. However, security failure does not automatically become a safety incident. The next step is system behavior. System behavior. The system might degrade, isolate a component, limit a command, reject an input, request human review, or enter safe state. The safety outcomes depend on how the architecture handles that failure. A well-designed system can contain a failure and prevent it from becoming harm. A poorly designed system can translate a small compromise into unsafe physical action. When a wireless or IoT component is compromised, the design question is, what prevents the system from moving into an unsafe state? So let's have a look at designing for degraded operations. Why degraded operation matters first. Degraded operation is a controlled mode in which a system continues to provide limited functionalities when normal operation is unsafe, unavailable, or no longer trustworthy. Wireless and IoT systems often depend on communication links, gateways, sensors, cloud services, and remote control. These dependencies can fail, and because of faults, interference, misconfiguration, or attacks. In ordinary IT, a failed service may simply be restarted or taken offline. In safety-critical systems, that may not be enough. Stopping abrupt may itself be unsafe. Continuing blindly may also be unsafe. Accepting untrusted inputs may create direct physical risk. The system should therefore move into a defined degraded mode with clear operational limits. For example, a device may continue measuring locally but stop accepting remote configuration changes. A controller may maintain a limited safe function but a stable automation that depends on uncertain data. A gateway may restrict traffic to essential messages only. The degraded operation is safer when it's designed, documented, tested, and understood before an incident occurs. Graceful degradation means that the system reduces capability in a controlled way, rather than failing abruptly or continuing unsafe operations. The aim is to keep the essential safety functions available where possible, while disabling, delaying, or moving non-essential functions to manual control. The degraded state must be visible. Operators should know that the system is no longer in normal operation. Maintainers should know which functions have been disabled, which assumptions no longer hold, and what checks are needed before normal operation resumes. Consider a medical monitoring device that loses its wireless gateway. A poor design might silently stop reporting readings or keep trying to communicate without alerting staff. A better design stores reading locally, alerts staff, and limits remote control functionality until the trusted connection is restored. The system has not solved every problem, but it has reduced the risk of unsafe behavior during uncertainty. Another method is fail-safe, fail-secure, and fail-operational. These concepts are important here. Fail-safe means moving to a state that reduces risk to people, equipment, or the environment. For example, a machine may stop movement, a valve may close, or a device may enter into safe standby state. Fail-secure means preserving security properties such as access control, confidentiality, or integrity. For example, a system may lock access when authentication fails. Fail-operational means continuing operation, possibly with reduced function, because stopping may be unsafe. This is common in systems where continuity is itself part of the safety. These goals can conflict. Looking at the device may be secure, but not always safe. Continuing operation may preserve service, but may amplify harm if the inputs are compromised. The correct behavior depends on the hazard, context, timing, and available fallback options. We end this slide by asking ourselves this question. When a security control fails, should the system stop, restrict operation, continue locally, or request human intervention? Another method for operation fallback is the local fallback and manual override. Local fallback reduces dependence on remote services during disruption. This diagram starts with normal mode, where operation may be supported by wireless communication or cloud supported or gateway or cloud service. A disruption then occurs. This may link to link loss, interference, or uncertainty about trust. The system enters local fallback. In this mode, it uses limited trusted operation, rather than depending on the failed or uncertain path. Manual override may then allow human supervision where automated decisions are no longer trustworthy. And the final step is verified recovery. The system should not return to normal mode simply because the link is available again. It should check the trust condition and check that trust condition has been re-established. Manual override is important, but it's not a free bypass. It must be controlled, authenticated, and logged. Otherwise, the fallback mechanism becomes another attack path. So fallback is not a bypass, it's a controlled operating mode with explicit authority, limits, and evidence. So let's have a look at the different mitigation patterns for wireless and IoT systems. We're going to first look at defense in depth. Defense in depth uses multiple independent control so that failure of one control does not directly expose the system to unsafe behavior. This is especially important in wireless and IoT systems. A system should not rely on one protective boundary, such as a password, one encrypted link, one gateway rule, or one network separations. Devices, wireless links, gateway, services, and data flow all need controls. Independent controls limit how far one compromise can spread. For example, a compromised wireless message should still face gateway validation, service-level authentication, application-level check, and safety constraints before it can influence a physical action. And the safety-informed point is that each layer should reduce the chance of a safety-relevant failure. And if you want to frame it from the safety-informed security, then each layer should reduce the chance of a safety-relevant failure. Defense in depth is not just more controls, it's layered control of how compromise can propagate. Now in this diagram, we can look at an example of layered control in an IoT system. At the device layer, controls may include secure boot and firmware integrity. These reduce the chance that the device starts from a compromised state. At the wireless layer, controls include pairing, encryption, and replay protection. These reduce exposure to unauthorized messages or manipulation over the radio channel. At the gateway layer, filtering, validation, and isolation can mediate traffic before it reaches service or safety-relevant functions. At the service layer, authentication, access control, and logging support accountability and control over commands, data access, and configuration. And finally, the safety layer includes limits, fallback, and manual override. This layer is essential because safety should not rely blindly on the same data path or control path that may have been compromised. The safety-informed view is that the system should not allow a compromised wireless message to become an unsafe physical action without any further check. You can also look at segmentation and isolation. Segmentation divides the system into control zones so that compromise in one area does not automatically spread to others. In safety-critical IoT, critical devices should not share unrestricted networks with general systems. A hospital patient monitor, an industrial controller, or a transport sensor should not be exposed in the same way as a guest device or a general office workstation. Gateway can mediate traffic between devices, clinical systems, or cloud services and maintain interfaces. They can also enforce authentication, filter commands, restrict protocols, and log access. The isolation limits the blast radius of compromised devices or credentials. So if one device is compromised, the attacker should not automatically gain access to every other device or system. Access should depend on identity, role, and device context, not location alone. For example, a hospital may separate patient monitor from guest Wi-Fi. The gateway accepts authenticated device traffic and logs clinical. In this slide, we bring together three different mitigation patterns: the authentication, the replay protection, and rate limiting. Authentication reduces the chance of unauthorized access. It helps establish who or what is sending a message. Replay protection reduces the risk that the old messages are captured and resent later. This matter where stale comments or stale reading could cause unsafe behavior. Rate limiting reduces flooding, comment abuse, and repeated unsafe requests. It can stop a compromised device or account from repeatedly triggering actions faster than the system can safely handle. This slide brings together three mitigation patterns: authentication, replay protection, and rate limiting. Authentication reduces the chance of unauthorized access. It basically helps establish who or what is sending a message. Replay protection reduces the risk that old messages are captured and resent later. This matters where stale comments or stale reading could cause unsafe behavior. Rate limiting reduces flooding, comment abuse, and repeated unsafe requests. It can stop a compromised device or account from repeatedly triggering actions faster than the system can safely handle. And the final row links these controls to the physical behavior. This is a critical point. In safety-critical IoT, messages are not just data. They may influence pumps, vehicles, alarms, locks, industrial processes, and clinical decisions. So the question is, can a valid-looking message still be unsafe because it's old, repeated, excessive, or outside the expected context? Let's now look at secure updates and configuration control. A secure update mechanism ensures that only authorized, authentic, and integrity-protected software or configuration changes are installed. Wireless and IoT systems often have long operational lifetimes. Vulnerability may be disclosed after deployment, and updates are needed to mitigate risk. However, update mechanisms themselves can become attack paths. If an attacker can push malicious firmware, downgrade the device, alter configuration, or interfere with update validation, the update system becomes a high-impact target. Configuration changes may also be controlled. They should be authenticated, logged, and reversible where possible. The safety-informed view is that a patch should not only be secure to install, it must also preserve the safety assumption used in the assurance argument. For example, a patch that changes timing, disable a validation check, alter sensor processing, or modify failover behavior may affect safety even if it fixes a security vulnerability. Let's now look at redundancy, diversity, and fallback together. Redundancy provides alternative components, channels, or paths for a function. Diversity reduces shared failure modes. Redundancy can help maintain service when a device, sensor, gateway, or communication path fails. In IoT systems, this may include backup links, alternative gateways, local control, secondary sensors, or parallel monitoring. However, redundancy alone is not enough. If all redundant components share the same firmware, the same vulnerable library, the same cloud dependency, or the same wireless protocol weaknesses, they may fail together. That is why diversity matters. Diverse components, paths, suppliers, configurations, or protocols can reduce common mode failure. Redundancy should support safe continuity, not uncontrolled continuation. A system should not continue operating through redundant paths if all available evidence suggests that the input or control logic is itself untrustworthy. Redundancy improves resilience only when it avoids common mode failure and supports defined fallback behavior. We now discuss voting and plausibility checking. Voting and plausibility checking are two different methods to ensure that some devices can be trusted. Voting compares multiple sources before accepting a value. Plausibility checking compares values or comments against expected physical operation or contextual constraints. Voting is useful when multiple independent sensors or inputs are available. If two sensors agree and one disagree, the system may reject the outlier, reduces confidence, or move into degraded operation. Plausibility checking is different. It asks whether a value makes sense in context. A sensor value may be correctly formatted, authenticated, and recent, but still be physically implausible. For example, a temperature reading may change too quickly to be credible. A medical reading may be outside expected psychological limits. A command may request a change that is unsafe given the current state. The safety-informed view is that a valid sensor value may still be physically implausible or unsafe to use. And in the redundant sensor decision, we can see the diagram here that shows a single redundant sensor decision process. In this process, sensor A and B report normal reading. Sensor C reports abnormal reading. The system does not automatically accept or reject the abnormal reading. Instead, it performs voting and plausibility checking. The decision may be to accept, reject, or degrade function. If the disagreement suggests possible sensor failure or compromise, the system may request manual review. Isolate the sensor, reduce automation, or use the safe operation mode. The abnormal condition is also logged. Logs provide evidence for the diagnosis, recovery, and assurance review. This is important because safety-relevant behavior should not depend on a single sensor reading, where independent evidence is available. Disagreement between sources is not just a data quality issue. It may be a sign of attack, fault, drift, misconfiguration, or even environmental change. We now look at common mode failure. Common mode failure occurs when multiple components fail through a shared cause, such as dependency, vulnerability, assumption, or condition. This is a major risk in redundant system. Redundancy may look strong on paper, but if all elements share the same weaknesses, the system may still fail as one. Sensors may fail together if they share firmware, calibration, or wireless protocols. Communication paths may fail together if they share a gateway, power supply, or cloud services. And similarly, software implementation may fail together if they use the same vulnerable library. Attackers may deliberately target shared dependency because this defeats apparent redundancy. Are the redundant elements generally independent, or do they fail together under the same attack or operating condition? In this slide, we show the fallback process for communication or sensor path. The primary path is the normal wireless link used during trusted operation. A problem is then detected. The problem can be loss, spoofing, or even jamming. Fallback should be selected according to safety need, not only availability. This is important. The first available path may not be the safest path. An alternative link may be slower, less secure, less reliable, or less appropriate for certain commands. The fallback path may restrict commands, sampling, automation, or remote access. The system then operates under a safe constraint with reduced capabilities and defined limits. Finally, there is a review. Return to normal operation requires confirmation that the primary path is trustworthy again. Fallback should preserve safety assumption, not simply reconnect through any available path. The next section is monitoring, detection, and response. We first look at monitoring in wireless and IoT systems. Monitoring analyzes communication, device behavior, and system state to detect abnormal or unsafe conditions. Wireless and IoT monitoring is difficult because devices may be constrained, mobile, intermittent, or physically exposed. Evidence may also be incomplete. Some devices may not produce detailed logs. Some communication may be encrypted or short-lived. The evidence may come from gateways, radio observation, logs, and operator report. No single source is likely to be sufficient. Monitoring should cover security indicators and safety-relevant behaviors. It's not enough to know that traffic volume changed. We also need to ask whether the change affects trust in system behavior. Detection is useful only when it triggers a defined response. A monitor that produces alert but does not influence containment, degradation, isolation, or recovery has limited safety value. monitoring should make degradation and compromise visible before they become unsafe physical behavior in an environment. So what are the wireless and IoT indicators? And here we separate wireless indicators and device indicators. Wireless indicators include signal loss or interference, association failures, unusual retransmission, and signs spoofing or replay. These may suggest jamming, disruption, misconfiguration, poor coverage, or active attack. Device indicators, however, they include unexpected traffic volume, changed command patterns, abnormal sensor reading, and firmware or resource anomalies. These may suggest compromise, fault, misbehavior, or abnormal operation. The indicators need interpretation. A weak signal is not automatically a safety issue. An abnormal sensor value is not automatically malicious. An unusual traffic pattern is not automatically an attack. The safety-informed view is that a weak signal, abnormal sensor value, or unusual traffic pattern matters when it affects trust in system behavior. So let's look at anomaly detection. Anomaly detection identifies behavior that deviates from expected communication, device, user, or physical pattern. Rule-based detection checks known thresholds, sequence, or safety limits. It's useful when the expected behavior is well understood. Signature-based detection identifies known attacks or malicious patterns. It can be effective against recognized threats, but less effective against novel or adapted attacks. Behavior detection compares current activities with expected system behavior. This can detect unusual activity, but it may also produce false positives. In safety-critical system, false positive and false negatives both matter. A false positive may unnecessarily degrade operation, interrupt service, or overload operator. A false negative may allow unsafe behavior to continue. So what should the system do when it's uncertain whether a behavior is malicious, faulty, or simply unusual? The system should move from detection to safe response. This diagram shows the sequence from monitoring to response in an environment. First, the system monitors traffic, logs, and signals. It collects evidence from communication devices and system data. Second, it detects an anomaly or compromise. Detection should trigger a response proportional to safety risk. Third, the system assesses safety relevance. Not every security anomaly has the same safety consequence. The system needs to decide whether the event could affect safety operation. Fourth is response. This may involve alerting, rate limiting, isolating, degrading, or requesting manual review. And finally, it records evidence and rationale. This matters for recovery and assurance review. After an incident, we need to know not only what happened, but why the system responded in this particular way. The idea from detection to safe response is that detection should be connected to safe response, not treated as a separate monitoring exercise. We then look at incident response and forensics. Incident response is a planned process for detecting, containing, investigating, and recovering from and learning from a security incident. In safety-critical IoT, incident response has an additional constraint. It must protect people and preserve evidence at the same time. Detection identifies alerts, abnormal behavior, or safety-relevant deviations. Containment isolates affected devices, networks, credentials, or services. Evidence preservation protects logs, captures, configuration, and firmware records. Recovery restores trusted operation after verification. Review updates, control, procedures, assumption, and assurance evidence. This sequence is important because response actions can themselves affect safety. Pulling a device online may preserve evidence, but it may also interrupt the safety function. Rebooting a system may restore availability, but it may destroy volatile evidence. Incident response in safety-critical IoT must balance operational safety, security containment, and forensic integrity. Let's finally look at recovery assurance, and residual risk. First, we look at recovery and restoration. Recovery is the process of restoring a system to a trusted and acceptable operating state after disruption, compromise, or degraded operation. Recovery is not simply restarting the system or reconnecting a device. A restart may remove symptoms without addressing the cause. A restored connection may still be untrusted. The system must be checked before it returns to normal operation. This may require firmware validation, configuration review, credential replacement, log analysis, and operator approval. In safety-critical context, recovery must restore both security confidence and safety confidence. Security confidence means that the system, device, credential, communication path, or even configuration can be trusted again. Safety confidence means that the system can operate within the safety assumptions again. A system should not return from degraded mode to normal mode until relevant trust assumptions have been re-established. So how do I verify return to operation? The diagram shows a verified return to operation. The process starts with an incident, such as an attack or disruption. The suspected cause of failure or compromise must be identified. The next step is containment. Affected devices, networks, credentials, or services may be isolated or restricted. Then the system is restored. This may involve patching, rebuilding, reconfiguring, replacing credential, or even rebuilding trust in a communication path. But the next step is verification. Before we go to return to normal mode, we verify the system. Restored component must meet security and safety conditions before normal mode operation resumes. Finally, the system returns to normal or revised mode. Return may be staged, restricted, or conditional. In some cases, normal operation should not resume until further assurance work has been completed. The safety-informed view is that recovery is complete only when the system can be trusted to operate within the safety assumptions again. The next slide is on assurance impact after an incident. Assurance impact occurs when an incident changes confidence in the claims, assumptions, and evidence, CAE, or controls used to justify system safety and security. This is an important point because an incident is not only operational, it may change what we believe about the system. For example, an incident may reveal that a threat was underestimated. It may show that a mitigation was weaker than expected. It may reveal that evidence no longer supports the original claim because the system has changed. And a mitigation may work technically but still leave an unacceptable operational risk. This means the assurance case should be updated when assumptions, controls, and residual risk change. The system should not keep relying on outdated evidence after a meaningful incident. An incident may invalidate part of the security or safety argument. And finally, the residual risk. Residual risk is a risk that remains after controls, mitigation, and recovery measures have been applied. No mitigation removes all risk. This is especially true in safety-critical IoT, where threats evolve, device age, environment change, and systems are updated over time. Residual risk should be explicit, justified, and accepted at the appropriate level. It should not be hidden or treated as an informal assumption. Safety-critical systems require evidence that remaining risk is tolerable in context. That context includes the operating environment, the users, the hazards, the available fallback modes, and the consequences of failure. Residual risk may also change over time. Risks that was tolerable at deployment may become unacceptable after a new vulnerability is discovered, or after a system update, or after deployment conditions change. What risk remains after mitigation, or who has the authority to accept it? That's a question that usually you should be asking. So if we look at the mitigation across the system lifecycle, mitigation is not a one-off deployment activity. It applies across the system lifecycle. At design time, mitigation starts with threats, hazard, and risk reasoning. The system should be designed with resilience, fallback, and assurance in mind. During builds, controls are implemented according to security and safety assumptions. At deployment, controls must be configured, tested, and evidenced before operation. During operation, the system must be monitored and maintained as threats and environment change. During review, assurance evidence should evolve with updates, incidents, and learning. During updates, patches and improvements feed back into design and assurance. This life cycle view matters because resilience can degrade over time. A system that was resilient at deployment may become fragile if updates are uncontrolled, logs are ignored, credentials are not rotated, or assumptions are not reviewed. Resilience depends on maintaining controls, evidence, and assumptions throughout the system lifecycle. And to summarize this lecture, resilience maintains acceptable, safe, and recoverable operation during faults, attacks, disruptions, or uncertainty. Degraded operations should be designed in advance with clear limits, fallback modes, and recovery conditions. Defense in depth reduces the chance that one compromised component message or control causes unsafe behavior. Redundancy and diversity support continuity when common mode failure is understood and controlled. Monitoring and detection can connect security indicators to safety-relevant system behavior. Incident response and recovery protect people, preserve evidence, and restore trust before normal operation resumes. Finally, residual risk remains after mitigation and must be justified, evidenced, and accepted. Safety-informed security does not stop at preventing attacks. It also requires systems that degrade safely, respond proportionally, recover with evidence, and maintain assurance over time. This concludes the lecture on resilience and mitigation. This is some key references that we suggest that you look at to further your understanding of the resilience and mitigation lecture. Thank you.